Hey guys, welcome back to Pop 'em Up Chem, and you're going to like this one. It's only a short one. We're still in Unit 9, 19 redox processes, and we're going to be looking at reactivity series today. Like I said, it's not going to be a very long one, more of an add-on, but I just wanted to have it as a separate video. Let's get right on with it. So in this video, we're going to be looking at the relationship between redox and reactivity, deducing chemical series from chemical observations, and using that reactivity to predict the feasibility of some reactions. As always, a little refresh question to get you started, which is using your skills of half equations to balance this equation here. Pause the video to give yourself a moment for that. Okay, fantastic. Let's go through that. So you don't want to go about this just by trying to balance the equation. You're not going to get the correct answer if you do that. We can see that we've got ions, so we're going to look for the redox half equation. So we're going to separate that out, and we can see that we have silver goes to silver plus, and that's obviously going to have an electron that is given out. And we've also got NO3 minus goes to NO. So using your priorities, we're going to balance first with water, and we're going to use 2 of those to balance the oxygens, and then 2 H plus on this side with 1 leftover electron. Now we can see that these equations already balance in terms of their electrons, so they cancel, and we can add them together, and anything that isn't in that top equation we can add in. So it's 1, 1, then we add our 2 H plus, and it's also 1, 1, and 2 H2O on the right hand side. Fantastic. Let's get on with the reactivity series then. Okay, so this is the reactivity series over on the right hand side. It's the same reactivity series that you get given in your data booklet. And first let's have kind of a qualitative look through the kind of order of this. So we kind of see at the top that there's a relationship between the groups and the reactivity. At the top we have group 1, then group 2, roughly. Again, there's some exceptions to this. As you'll see, there's some group 1 elements mixed in there. Then we have aluminium from group 3, carbon from group 4, and then we have the transition metals, followed by hydrogen, and then unreactive metals, and the precious kind of jewelry metals at the bottom. So if we think about being closer to the left-hand side of the periodic table in group 1, those are the elements that most easily lose electrons, and that's because they have the least number of electrons in their outer shell, so they're happy to lose those electrons. So it probably isn't surprising then that we can say that elements on that side of the periodic table are more reactive, especially when we think about reactivity in terms of how easily these elements are oxidized. And that's because the more easily they give up electrons, that's the thing that's going to cause the reaction to happen, the more easily they're oxidized. And so group 1, group 2 are more reactive than as we go across. Now, we don't want to get confused and think that as we go across or as we go down the reactivity series, that it becomes more easy to reduce these. It's not necessarily the case. It just means that they do not oxidize as easily. So it's not the opposite case. It just means that the things at the top of the reactivity series are oxidized very easily and are good reducing agents, and the things at the bottom don't react at all. Now, if we want to look for good oxidizing agents and things that are reduced very easily, we'd want to look at non-metals. So think about it, that makes sense, right? Because these things at the very bottom of the reactivity series, they're not good at either. And that makes them great at what we use them for. If we look at these metals down here, gold, silver, platinum, copper, these are all jewelry metals, or they're used in places where we need corrosion resistance. So there's a reason that gold has been used for money for thousands of years, and even in simple things like wedding bands, gold is often used because it's a symbol of lasting value, and I suppose meant to represent something about the nature of your future marriage. Because there is corrosion resistance, the gold is going to be around for your children and your children's children to admire in the same way. We can use the reactivity of metals to help us find the outcomes of displacement reactions, because in a displacement reaction, the more reactive metal, the better reducing agent, will always displace the less reactive metal. And we can use 3 different methods to find if a reaction is occurring. So we can have a color change, temperature change, or release of gas. So let's take this example of copper sulfate, which is blue, reacting with zinc solid. Now, that will form zinc sulfate and copper metal. Now, in this example, if we think about the reactivity of the metals, because copper is right down at the bottom of our reactivity series and zinc is higher, that means zinc will displace the copper. And so we can observe that in this reaction, because copper sulfate solution is blue, zinc sulfate solution is colorless. And we can go further and break this down into the component half equations, and we can see that the oxidation state of copper in the reactants is 2+, and in the products it's 0. So we do copper 2+ plus 2 electrons equals copper. And we also have zinc, and for the other half equation, we'll have zinc solid, which has an oxidation state of 0, goes to zinc 2+, which of course is going to need 2 electrons to balance the charge of that half equation there. Now we could also then combine those to form the redox equation, just like we did in the previous lesson. So we can think about using this understanding to think about how these reactions might occur. So let's say we were going to do some reactions. So we were going to react magnesium metal with all of these following salts: magnesium sulfate, zinc sulfate, iron sulfate, and copper sulfate, and then do the same with zinc metal, iron metal, and copper metal. We would be able to make a prediction using the reactivity series on the right hand side. So for example, let's have a look at magnesium mixed with zinc sulfate. Well, magnesium is right up there in the reactivity series, zinc is further down, so we would indeed have a reaction there. So I can put a little tick there. So you can have a go at copying and completing this table just by using ticks and crosses for where reactions would not occur. Pause the video and give yourself a moment to try and complete that. Brilliant. So hopefully you got something that looks like this. And that shows that you have magnesium displacing all of the other metals from the salts, and zinc doing all of them except magnesium, iron, only copper, and copper not displacing any of them. To integrate this further with what we've done in the previous lessons, try and write some ionic symbol equations for each successful displacement reaction, and write balanced equations for the reactions that do occur. Pause the video and give yourself a moment for that then. Brilliant. So let's go through a couple of the ionic equations. So we're going to have Mg plus Zn2+ for the example of the first reaction goes to Mg2+ plus Zn metal. And that same structure, because these are all 2+ metals, is going to continue down that column. So we're going to get Mg plus Fe2+ goes to Mg2+ plus Fe solid. Now, I won't go through all of those now, but if you're struggling with making the half equations, putting them back together to make the ionic redox equation, then go and check the video. I'll link that in the description for how to do redox equations. Next, writing some balanced equations. So this is also very simple, just the same thing as above, but we're including the sulfate ion to give a full balanced equation. So we'll have magnesium plus magnesium sulfate goes to magnesium sulfate plus zinc. Now, you just do that again, very similar for all of the different ones. So not a very long lesson today, guys, but you're still going to want to make sure you do some questions to make sure you understand it fully. remembering that more reactive metals are better reducing agents and more reactive non-metals are better oxidizing agents. Thanks for joining me again. Thanks for all the feedback and support I've been getting. I really appreciate it. Comment below to suggest new content, like, subscribe, hit the bell icon, share this video, share this channel, and share the other channels, which will be in the description below. And as always, practice makes slightly better.